Hi, everybody. Welcome to today's Still Connect Classroom webinar. We appreciate you joining us, and we're so happy to have David Brewer with us today. Want to remind you that this is being recorded, so the recording will be available, and we will send you the slides along with that. And there are two handouts to the right in your little right sidebar that are talking about some solutions that we will discuss in the webinar today. These webinars focus on reliability maintenance and of course proper sealing, and they're educational for anyone who would like to attend. And we invite anyone across the industry to send us topics that they would like to have us talk about, and also tell us what you think of the webinars and ways we can improve them. During the webinar, you can ask questions in the question tab that is also in your sidebar at any time during the presentation. And any kind of question is open, so just let us know what you any questions you have and what you'd like for us to talk about. And David, thank you for joining us today. I want to ask you a question before we get started and as we let everyone join. What is one of the toughest applications you've dealt with in general, or when it comes to water conservation?
Yeah, so thanks, Lori. I would say one of the toughest I've ever seen is the black liquor evap pumps. Those black liquor evap pumps can be a bear. They have everything from the stuffing box sees anything from a full vacuum to full pressure, and they always pose a hard problem. You cannot introduce outside water into that process, or else they're just defeating the whole purpose of the evap pump. So it always poses a hard, a tough problem, and I think during this webinar we're going to be able to go over that.
Yeah, if you're trying to evaporate something, you don't need to add water to it.
That's right. That's the defeat the whole purpose.
Well, great. Well, I'm going to let you get started with the presentation, and if you need anything from me, let me know, and we'll get started. And guys, remember to ask questions in the question tab as we go along. Thanks, David.
Thank you very much, Lori. I appreciate it. Again, guys, in that tab, if you have anything during this presentation that you want repeated or have a question on, please don't hesitate to type that in, and I'll either reiterate it or go back over it so you understand it better. But so my name again is David Brewer. I'm the Atlantic Regional Manager for SEPCO, and I basically cover from Delaware south down to Fernandina Beach, Florida, and as far west as Chattanooga, Tennessee. So I am always available for any type of questions. And if I don't know the answer, I'm going to get it for you. I'll find out for you. So with that, let's get started. So today, what we're going to do is we're going to go over, as Lori had talked about before, water conservation now is like the key topic. It's a big, with corporate teams, the big paper industry, corporate guys, ethanol, you'll see in here, petrochemical, things of that nature. Water conservation is a big deal. So today we're going to go over, water loss from different types of seal technology, how that water can be lost, where, from improper installation to damaged equipment. You're going to understand, unneeded dilution. I mentioned the evap pumps before, and we have a very specific example of that where we show you where they're trying to evaporate water off of a process in order to make a finished product out of it. So we're going to go over that. We're going to have a case study for the pulp and paper industry as well as the ethanol industry, and you'll see where this technology that we're talking about, or this type of maintenance practices, can be used in water conservation. So Lori, I'm going to hand this back over to you to ask this question, but we've got a poll here before we get started.
Yep, I will launch it right now, and we'll give you all about 20-30 seconds to answer. So, are you being asked to conserve water in your plant or facility? And leading question, of course. But yeah, please answer. We'll give you a couple more seconds, and then we will close it and get the results. And no surprise, 100% of the folks on the line are being asked to conserve water, and that's why we thought this was such a timely topic. And David, back to you.
Okay, great. Well, thank you. You know, again, that's no surprise. You know, this is a great lead. That poll's a great lead into this, in a sense that everywhere I've been here recently, we have been asked, you know, is there any way that you can help conserve water for us? You would never think that in today's industry, that especially when they deal with millions of gallons of water a day in a paper mill, a chemical plant, an ethanol plant, in their process, that sealing water is such an issue. But as you'll see as these slides go along, that within this industry, as stuff in boxes leak, as water gets dripped out onto the ground, or maybe even diluting the process, you're going to be talking about excuse me, millions of gallons per pieces of equipment per year. So we're gonna focus on that, and we're gonna kind of show and pinpoint where to look for these problems and how to solve them. So some of the sources for, you know, unnecessary waste. If you look at like you know, stuff in box leaking, all of you are probably very familiar with packing and how packing works, but when you walk by a pump and you see that a pump or a piece of any type of piece of equipment is operating, whether it's an agitator or a mixer, or again a process pump, you'll see the product or the dilution, which is water, that will be leaking out of the stuffing box. That's going to be some of the waste that we actually address. You're going to see, you know, you'll understand like how does shaft deflection, how does it affect packing, or how does it affect a mechanical seal for that matter? Whether or not proper lantern ring, whether the lantern ring is in the stuffing box properly. You know, we get those stuffing boxes, and when we teach classes out in the field, is we want people to understand exactly where that lantern ring goes, because there's a port that comes in. That port is effectively so necessary for that lantern ring to land within that port, because again, we'll go over why, but the lantern ring delivers the water to the proper packing. Damaged or worn shafts and sleeves. Not only does like a shaft that's got an apple core in it affect whether or not the packing or the mechanical seal for that matter is working effectively. If you notice sometimes when pieces of equipment come back from repair, somebody has either bored out the stuffing box or maybe even built up the shaft sleeve to be a little too big, or bored out the stuffing box too much, and that can be in that category as well. And if the relationship to the OD and the ID of the packing does not match, then you're going to have problems and you're going to have leaking packing. Process dilution, this is a huge one. This is where, you know, we were talking about earlier, where you've got water coming through the seal or through the packing into the process, and it is diluting the very product that they're trying to evaporate that water off of. I'll give you a good example. In the liquor situation that I mentioned earlier, what they're doing in a paper mill is they are trying to get that black liquor to a point where they can burn it, because they use it for a source of fuel. So you can imagine from different stages of the evaporation process, that liquor's getting heavier and heavier and heavier until they get it to about anywhere from 67 to 73% solids, so they can spray it into the furnace, and they burn it and use it as a source for fuel. And other processes, they evaporate water off of, for instance, plastics and petrochemical and stuff like that. They're evaporating that water in terms for their final process. So we're going to talk about process dilution and why that's so important. And seal chamber evaporation, that's a very specific thing to when there's a case study in here where we're going to show you in the ethanol industry and the petrochemical industry where that's so important, that seal chamber evaporation. So where are you going to find stuff in boxes? So all over the plant, guys and girls that are listening to this, that there's so many pieces of equipment that you might walk by that you look at, and you don't realize that piece of equipment might have a stuffing box. In the paper industries, everything from hydropulpers to mixers to agitators. And the petrochemical business in the ethanol industries, again, mixers, agitators, augers, things of that nature. But sometimes you will see massive pieces of equipment that have 12-inch shafts, 13-inch shafts. Don't ever be shy from going after those as well. But they use tons of flush water in order to keep the process from leaking out to atmosphere. And they use the flush water there to keep that from coming out. So we have to make sure that the Fluid Sealing Association of America dictates that 10 to 12 drops per inch of shaft size. So if you have a 10-inch shaft, you're going to leak, or excuse me, a 1-inch shaft, you're going to leak 10 drops per minute roughly. And as that shaft gets bigger and bigger and bigger, that stream of water, flush water, is more acceptable to come out. But about 10 to 12 drops per inch of shaft is what the FSA says. And that's what our ultimate goal is to get to that number. And once we know that, we can control the flush rate, and we can help the mills or plants or what have you save water. So one of the first things I want to talk about is shaft deflection. I know all of you have seen where you've got a solid shaft and it's rotating inside of a stuffing box. The first thing it has to be concentric, meaning that shaft has to be going through that stuffing box right in the middle. And if that's the case, you've got good maintenance practices. So for instance, when a plant, when they rebuild a pump or a power frame, most recently here, we've had a situation where we were doing a refiner, and that we had to make sure that shaft was going through the stuffing box right in the middle. You don't want to start out somewhere between 72 to I've seen it as from 72 to 50 thousandths out of the center of the stuffing box. Because if you start out in a bad position, then it gets worse as that shaft starts to turn. And the bigger the journal, the worse the problem. And what that does is when shafts, when they deflect, when they move out around and when they deflect, they wallow out the packing, meaning that, as you can see in the picture here, where when the shaft bends one way and the packing goes the other way, you're going to create a leak path there, and you have what they call a pressure drop in that situation. And when you have a pressure drop, the flush water actually pours out of the stuffing box. The other thing that I wanted to mention here is, not only is this in effect for packing, it's in effect for mechanical seals too, because you can imagine mechanical seals are loaded by springs. They're loaded by spring, and then the faces have to remain together. So when that shaft deflects, it actually fatigues the springs, and if it fatigues the springs, then you're going to cause a problem in the long run. You'll end up losing either the outboard or inboard seal on say a double seal. But one of the things we're going to talk about here in just a minute. Another thing that to consider, when you're looking at packing specifically, this is in regards to packing a stuffing box. What we find a lot of times out in the field is we see when we're troubleshooting applications, we will pull out a set of packing, and inevitably what we see is a clogged or blocked lantern ring. And what that means is over time that piece of equipment is operating, and because you're at a certain flush pressure, and typically when outside source water is concerned, what happens is there's one seal water pump that supplies, let's say, 10 to 15 pieces of equipment. Well, when one of those pieces of equipment go down, or the packing or mechanical seal fails in it, you'll have a pressure drop in the system. And when that happens, inevitably the pressure drop in that system will cause the process side of the equipment to overtake the flush system, and it can clog a lantern ring and plug the holes. Well, what happens when that happens is you end up with what we call, it overheats. The seal water cannot get to the packing because the lantern ring is the delivery system for the flush. And if it's plugged, it cannot get to the packing to cool it off. For all intents and purposes, packing will hydroplane on the flush system. That's the ultimate goal. Well, in this situation, if the lantern ring is plugged, then you cannot get the flush system to the packing to cool it off. And so therefore you'll end up with, what we're going to talk about here in a minute is worn equipment. And once we get that equipment worn, the leak paths just increase from there. And here we go. So you see, everybody probably looking at this webinar has seen this, where you have a shaft or sleeve damage. And sometimes in the field, we'll call it apple coring. We'll call it, there's all sorts of different names for it. But what happens here is you have a worn spot in the sleeve or the shaft where that packing goes. And what that does is it actually it changes the relationship of the packing in the stuffing box. And what I mean by that is it changes that relationship from the OD to the ID. So if you were putting, let's just say, 1/2 inch packing inside a stuffing box, and you're going to put a mechanical load on it, if you have wear on the ID and it's worn considerably, you've changed that 1/2 inch packing potentially to what now needs to be 5/8 inch packing. So when you do that and we see this wearing, that's when you're going to get excessive leakage. So if you've got a flush system coming in and you've got an open gap on the ID, wherever that gap is, if it's on the ID or if it's on the inside portion of the packing or the outside portion of the packing in relations to the process or atmosphere, you're either going to get leaking to the inboard to the process, or you're going to get leaking to the outboard to atmosphere. Either way, that's wasted water. That's wasted process water, in the sense that when it comes in, it's got to go somewhere. And if you don't have the right relationship between the OD and ID of your packing, that's going to cause a problem. And one of the biggest things that we see out there today, you won't realize it until we'll show some numbers here in a little while, but what you don't realize is when you dilute process, if you dilute the process, and this can pertain to liquor, it can, in the paper industry, it can pertain to ethanol in the ethanol industry, or what they call, a mash slurry or what have you, and condensate pumps. I see this a lot. Anytime you introduce a diluted process or water into the process, you're diluting it. And condensate, for instance, in every mill or plant, doesn't matter what type of mill or plant it is, has what we call condensate pumps. Condensate is a precious commodity in today's industry, and you cannot dilute condensate. You cannot bring in an external source of fluid and then introduce, if you fail a set of packing or if you fail a mechanical seal, it cannot be introduced into the system. One, because the temperature is different from what is being pumped, and two, clean condensate is a lot different than non-potable water, and so you will foul that system. And if you foul that system, you don't want to be the person with that on your resume. But the idea is to either use, one, the product being pumped to save, or two, you'll have to use an external barrier fluid, and we're going to go over that here in just a minute as well. Seal heating evaporation. So this is very specific to certain types of equipment, specifically petrochemical and ethanol. And what happens here is where you have to use an external barrier tank. So for instance, and I'm going to show you later how these tanks get set up properly. But you have to have a barrier tank with a double seal. This really pertains to a barrier tank with a double seal. And what they're telling you here is that barrier tank and that barrier fluid has to be compatible with whatever you are pumping. So for instance, everything has a different flash point. Water has a certain flash point, liquor has a certain flash point, ethanol has a certain flash point. It doesn't matter what it is, but everything that we deal with in process equipment today has a flash point to it. So you could imagine if friction equals heat and then heat equals wear, you could imagine that when you are using a double mechanical seal and you're injecting an external flush or an external source of fluid into a mechanical seal, it stays in that little chamber. Well, that little chamber you create friction and heat in that chamber. Now, if whatever you're using as a barrier fluid is not compatible with a certain amount of heat that you're generating, it's going to flash off. And when it flashes off, it turns from a liquid to a gas. When it turns from a liquid to a gas, it expands. And so we're going to talk about that as well here in just a second. So what we're going to go over is, in the stuff and box and seal chambers, there's 5 processes that can help prevent water loss. And given those examples that I just named, those small little examples, we're going to kind of show you guys how those 5 things can affect stuff and box reliability as it relates to water conservation. The first and one of the most important things, we do these classes all the time where we like to specifically go into the mills, into the plants, and show their mechanics the proper way to install packing. One of the things that people don't realize is when packing is manufactured, when mechanical packing is manufactured, it's actually a little, and when I say a little, like a 32nd inch shorter than it is lengthwise. And the reason they do that is so that when you put a mechanical load on it from a gland follower, you have to radially expand that packing. And that packing has to radially expand to the point where on the bore of the stuff and box, it creates a gasket. And on the sleeve and shaft, it creates a dynamic seal. So if you have 5 rings of packing in the stuffing box, and then you have a mechanical device like a gland follower pushing against it and creating a load, a mechanical load on that packing has to radially expand through the entire set. And if it expands through the entire set, it'll do its job properly in the sense that it will seal. Every single ring will be effectively a seal, as you go forward. But it is imperative that you do that. When we talked about when we talked about wear early on in this presentation, when you see wear at the very top of a stuffing box, so let's say you unpack a set of packing out of a pump, and at the very top of the stuffing box, those first 2 rings you pull out are extremely thin, burnt. They're in terrible shape. And where those 2 rings were actually placed, you see polishing on the sleeve or the shaft. And what that indicates is that packing did not load all the way across the set of packing. It only loaded right there at those first 2 rings. Now, again, if it only loads right there at those first 2 rings, the bottom rings aren't doing anything but just sitting there. So you can effectively have a flush water coming in from an external source, and it would be unencumbered to the ID, meaning that it would be coming straight into the process or to the pump, to the flush port, and then it would either be going straight to the process or it'd be coming right out the discharge side of the flush port. So that's why it's so important to get each ring seated properly, and there's tools out there to do that. Now, the precision installation of a mechanical seal, again, it couldn't be more important. When you look at a mechanical seal today, people take it out of the box and it looks like, something that they're just so, it intimidates them. But through proper selection, through proper installation procedures, a mechanical seal can be as effective as anything out there, that seals a stuffing box in the marketplace. We'll properly help you inspect the stuffing box, make sure that the shaft is concentric to the bore of the box, make sure there's no in play, meaning radial thrust, the bearings are good. You really have to make sure that you train the guys at the facility properly about seal installation. You don't want to put a mechanical seal, because standard mechanical seals right out of the box can only take 3 to 5 thousandths TIR, either on the thrust side, which is back and forth, or the axial way, which is axial runout. And so you want to make sure that those mechanics understand what that mechanical seal can do, what it's capable of, therefore, and then how to set up the proper environmental controls. That's whether it has a barrier tank, whether it has an external flush system, but you want to make sure that they understand how to properly set that up. But one of the things that you'll see out there, cartridge seals have come so far in the last 20 plus years. I remember starting off in this business 26 years ago, and back then, basically, they had cartridge seals, but they were relatively new to the marketplace. Nowadays, with cartridge seals, everything is a little more simplified. You put everything in place at one time, and there's a few maintenance procedures that you have to document before you get that seal installed. But cartridge seals certainly do help with ease of installation these days. So the appropriate flush arrangements and the way to set these barrier fluids up, barrier tanks or barrier fluids up, there are 100 different types of environmental controls, from everything on packing, where you have an external flush coming in, you have a ball valve to set the proper flow, and on the discharge side of the ball valve, you can actually set up how much positive pressure you want in that stuffing box. You can set that up with a mechanical seal as well. There are barrier tanks that we like to look at, in a situation where you absolutely cannot introduce water to the process. You put a barrier tank there with, a certain type of barrier fluid. We have all sorts of barrier fluids. There's just hundreds of different barrier fluids on the market that you can use in certain process that are either chemically inert, they can handle extreme high temperatures, extreme low temperatures, and that they are good lubricators. And that's a big thing as well, is how well does that fluid in that barrier tank, how well does it lubricate? Meaning, like, certain things when they get super hot, they get really viscous. Believe it or not, hot water is a terrible lubricator. But something like an ethylene glycol, a propylene glycol, or sorts of blends of that nature, or a mineral oil or whatever, it might be a better barrier fluid that you would put in a sealed pot that would be beneficial to, if that inboard seal failed, it would not contaminate and ruin the process or the product that's being pumped. Proper setup of certain controls. We want to know when we put these things together, there's bells and whistles that go along with some of these environmental controls that can let us know, hey, look, your inboard seal has failed. It's not working. And so right now you're just dumping water or whatever into the process. And we've got things that can, they out there that can tell us that can tell us, hey, you've had a pressure drop. Here's what you need to do. You need to shut that pump off. You need to fix that, fix that mechanical seal. Things like, make sure that we've got the right, the lantern rings don't get clogged up, that they're operating and working properly. There are all sorts of different tools out there to indicate that as well. one of the big things that when I do training in classes today, when we do a lot of training out in the field, and when we do, we want their maintenance guys to understand the relationship between loading a gland. When I say loading a gland, I'm talking about taking a wrench and actually tightening the nut that and the fastener that brings the gland follower in, that loads the mechanical packing. And not only just the installation of the packing and how that packing works, internally, we also have to make sure that adjustments are made over time. And when adjustments are made over time, as what's going to happen with mechanical packing, no matter what, packing is going to eventually, it'll wear. It has to. It's a textile. And so over time, as it wears, you're going to have to, or the plant person is going to have to make an adjustment. And when they make an adjustment, that gland gets tighter and tighter and tighter. But what we advocate for when we do classes and when we teach our maintenance people out in the field how to properly care for a stuffing box and the proper way to conduct stuffing box reliability is we want them to tighten these gland followers one flat at a time, maybe two flats at a time. And the reason for that is because certain textiles that we use in packing, doesn't matter who it is, what it is, certain textiles will transfer heat differently than other textiles. So for instance, a carbon yarn or a graphite yarn has a much higher surface speed than a Teflon yarn or an aramid yarn like a Kevlar or something like that. And the relationship between how that gland follower is tightened and how much that heat that packing can transfer heat is different from product to product. So we want everyone to understand and know that gland follower is there for a reason. It has to be tightened over time. But at the same time, we want the people to understand that tightening that gland follower does have a repercussion. You can't just come in, tighten it 3 or 4 turns, and then walk away, because you're going to burn everything up. And once you burn everything up, it glazes, the packing will glaze, and then the flush water, again, that's being used to cool it, will almost always start flashing off, or it'll just come pouring right out of the stuffing box or going right into the process. And we want to be able to understand the people that they're using our products or anybody's products to understand the relationship between that packing follower and that packing and how it's being used. Shaft stabilization, as we talked about earlier, is very important. When we talked about deflecting and stabilizing a shaft, excuse me for 1 second, I'm just going to take a real quick swig of water. There we go. That's much better. As we talk about shaft stabilization and how do we keep that shaft centered in the stuffing box, there are many different types of ways to do that out here. The first thing you have to do before you do anything is when you're rebuilding, when the customer or the plant's rebuilding their equipment, they need to make sure the bearings in the power frame are good. We want to make sure that those bearings are actually brand new in the sense when they come back and rebuild a piece of equipment. But the other thing we can do is if we've got long overhung shafts, like mixers, agitators, hydropulpers, big augers, things of that nature, we want to make sure. And what happens is the bearing could be 3 to 5 feet away, from the stuffing box. So you've got that long overhung shaft, and it has a tendency, because it's got a blade on it, and that blade's turning with that shaft, that it can wobble, and it has a tendency to wobble. Well, in order to change that, there's certain products out there that actually you can stabilize the shaft inside the stuffing box, and through things big high temp thermoplastics that are extremely stable. thermally stable, that can handle any kind of, type of chemicals, that go 0 to 14 on the pH scale, but have bearing quality characteristics and have very low coefficient of frictions. So good thermoplastics that have, a carbon graphite filler in them or something like that, you can put those in the bottom of stuffing boxes, and you can keep those shafts from deflecting and keep them steady. And when we do that, what happens is we don't change that OD-ID relationship with packing or even a mechanical seal. We keep the springs from fatiguing. We keep the packing from getting knocked around in the stuffing box. And in total, one of the most unintended consequences from this stuff is it actually helps conserve water, because you can imagine if that packing always stays in place, or that mechanical seal always stays in place the right way, that the water that's being used to flush it, it remains at the steady, 10 to 12 drops per inch of shaft OD and ID size. Same with the mechanical seal. I think I failed to mention early on, but a mechanical seal they all leak, but they leak in terms of parts per millionths. They don't leak in terms of drops per minute or anything like that. I mean, so we sometimes deem it as invisible leakage. And so when we have a way to stabilize the shaft to keep those springs from fatiguing, or in the case of packing, to keep the packing from wallowing out per se, those shaft stabilization bushings are great for to help with that. So the next couple slides, guys, I'm going to be able to give some really cool case studies that we'll be able to show you, where we actually save water, where we actually help the customer. And this will maybe give you guys ideas where it might be able to help you in the future. So Lori, I'm gonna hand this back over to you real quick for a poll, and then we'll get back to it again.
Sounds good. We just want to know how many of you are collecting water use data or other general plant data, because as you'll learn as David moves forward, data is important. So you have a little bit of time left to answer. So far, no one's voted yet. So can we have one person vote? Silence is deafening over here. So we're not getting any engagement with this poll, but that's okay, because if you're not collecting data, I'm sure that at this point we would recommend that you do so, and we'll just move on to the next slide.
All right, good deal. Before I go further with this ethanol poll, I did want to share one thing with you guys. Here just recently, I was with one of our distributors, and we were in a plant that was getting ready to install flow meters on their big 12-inch lines that are coming into their plant. And they will get from that, they will get a data point. And these aren't lines for each individual pump. These are flow meters, these big, massive industrial sized flow meters that that they can get a reference point of how much water they're bringing in total. And then on top of that, be able to, from there, we can hopefully gain data from each individual pump. And from each individual pump, we'll be able to tell, all right, we'll have at least a ground point. We'll have a data point in which we can start from, and then we can say, hey, from this 40 million gallons of water that you're consuming, over time, we're going to be able to say, of that 40 million, we saved you 2 million or 3 million or whatever it might be in total water savings. And that's the whole idea. So what you'll find out as we go forward is data is king. We want to make sure that we understand where we started from and where we're going. And as long as we get data, you can never have too much of it. As long as we have data, we'll know where to go to. Sorry, guys. Just trying to keep my as you talk, my throat gets scratchier. But anyway, so with this ethanol case study, what we had was a plant engineer. They were struggling with some pumps, specifically slurries, where they were using double mechanical seals, and they had just external flush coming into a header, then into the mechanical seal. And where they had problem was they couldn't tell if the inboard seal was leaking or not. There was no way for them to know if they were getting any intrusion into their product. Well, as you can imagine, as these slurries go, they're trying to get water off of that process. That's the whole goal of some of these big mash slurries and stuff like that. And if you've ever been in an ethanol plant, the one thing you would see is in ethanol, inside of one ethanol plant, there's 3 types of different plants. I mean, they have a byproduct that's sold as this, and the pure ethanol is not the ultimate main goal. They have different byproducts of the process. And so in understanding this and knowing this, we were able to help him set up the environmental controls properly, look at premature failure and why was that happening, and then train their people. Hey guys, look at this next time and help understand how do you put this mechanical seal on properly, and why we do the certain things that we do. So the first thing that we did, is when again, I'm sort of being redundant here, but he had a hot, sticky fluid that was actually, was a big slurry, and their whole idea was they were trying to take that and they were making a byproduct out of it, in which they needed to get the water off of it. They were evaporating the water off of this process, not just to this ethanol one specific slide, but I wanted to mention to you guys, I actually have another end user that in an acid plant was trying to take water off their process as well. And so very similar application, a slurry, it was sticky, it was a mess, and we had to help them get the water off of the process, or from entering the process, so that they could move forward. But as you can see, as inboard seal leaks, and if you don't have the proper environmental controls, you just don't know, and you don't have control over the flush that's going into the system and diluting your product. So one of the things that we when we look back on this, again, I'm sort of being redundant here, but when we look back on it, and you've got a hot slurry, you've got to take into consideration, you've got face materials, different types of face materials. So in a slurry application where the equipment's moving and there's a potential of the slurry getting inside the seal faces or on the mechanical seal itself, you have to know what types of material to choose. For the ones of you there that have sold mechanical seals, that one mechanical seal, I'm going to 1 3/4 inch mechanical cartridge seal, double cartridge seal, it could have 20 different types of face combinations, 10 different types of O-ring combinations. You have metallurgies to consider. You have everything from, everything to consider when you're looking at that. So when you guys come to us and you say, David, Terry, Zach, Steve, whoever, I've got this application, the first thing we're going to say, well, what are you pumping, or what are you mixing, or what are you agitating, or whatever, because the first thing we need to do in our brains, it's just kind of like geared in there. All right, we need to know if we're going to use carbon faces, carbon versus silicon carbide, or silicon carbide versus silicon carbide, tungsten, on and on and on and on. And what type of springs do we need? Do we need a single spring? Do we need multiple springs? Those are the things that we consider when we look at each application. We need to know there are a lot of questions that we have to have answered, and that's part of the selection process. In this situation, we were able to, between understanding what they were trying to accomplish, that one, we knew they did not want water in their process. That was a no-no. That we had to get rid of that water. That was the biggest thing. Two, we wanted to make sure that the longevity of the mechanical seals went from one time to another time. So in this case, it went from 15 months where they were, their normal seal life was their what we call mean time between failures. That was from a 15-month period to a 37-month period. So we more than doubled it. And the way we do that is, so in this case, we needed a double seal that had a barrier fluid tank. Instead of an external flush, we had a barrier fluid that was compatible with the material that they were pumping, the process in which they were pumping it. But in this case, we had to know that, hey, we need to make sure that fluid in that seal, as it transfers from the barrier tank through the mechanical seal, that mechanical seal stays at a certain temperature. So we were able to, put a pumping ring in there. That pumping ring helps facilitate the true convection of the tank. But in the other thing, we had to make sure that we use the right fluid. So in certain cases, I hate to use names, but sometimes you can use certain barrier fluids, a mineral oil or a sort of an ethylene glycol, propylene glycol type mixture or something like that. But something that's compatible with the process, if in fact the inboard seal fails. You can imagine if the inboard seal fails, if you just had water going in it, it's just nonstop. It would go until you shut it off, and you wouldn't know. How would you ever know it failed? There'd be no way for you to know that it failed. In this case, if you add a barrier fluid tank, a convection tank, you would be able to tell, because of the way you set that tank up, you would be able to tell whether the seal failed, the inboard seal failed or not. See, that's the one thing that people don't really understand about double seals, is it's hard to know on a double seal, because if nothing's leaking to atmosphere, how would you ever know that you're just dumping water into the system? Because there's no glass, there's no way for you to tell on a traditional external flush system. In this case, we've got a sight glass on a barrier tank that you'll be able to look at from time to time to know where your barrier fluid is in that process. And what that is it's just true convection. That barrier tank, the fluid is coming in, it goes into the mechanical seal, it gets pumped around, and then it goes back to the barrier tank, and then is reused again. It's cooled with cooling coils, or we have other ways of doing that as well. But yeah, so there's a definite way that you'll be able to always tell that tank is just truly convecting, and it's doing its job. The other thing I want to make sure before we, sorry, Lori, that's my fault. I did want to mention that where you put your barrier tanks is also extremely important. And once you see this, you'll realize it. If you ever go around from plant to plant and you look at different pumps and different processes, you'll notice that sometimes there's a barrier tank and it's head high, 5-6 feet high in the air. It's 10 feet away from the pump, and you've got this huge long plastic line coming back to it. I just want to warn you guys out in the field, if you look at any type of the API guidelines and what have you, a barrier tank is only supposed to be 24 inches away from the pump. I might be over exaggerating here, but it's like 2 feet away from the pump, 18 inches off the center line of the pump, and you're supposed to set it up from the coils or the line coming off of the clockwise position, so it has a better chance of convecting temperature and heat the right way. But if you do this and if you set this up properly, you'll go from like our guy did here, 15 months to 37 months, and you're not introducing water into their process and making them evaporate that water off of it. All right, so that was ethanol. This one's a great case study in pulp and paper. And what these guys wanted to do was their biggest thing was they were pulling off of an aquifer, and their lease was running up. They had to show the people who ran the aquifer. They had to show them, all right, we're going to be good stewards of the environment. We're going to start conserving water we're going to show you how we're going to start conserving water. And this is where we come in, and we're able to document these kind of water savings for them and show them exactly how much water they can conserve. So one of the things was, that previous slide had mentioned that this was a brown stock pump. It's very common in the paper industry. You see, brown stock pumps, bleach stock pumps. Stock pumps are a very common pump inside a paper mill. And I'm sorry, Lori, can I move? I need to move one of my things so that I can see. I apologize, guys. I'm having technical difficulties. There we go. So one of the things that we were able to do, and you can do this through a flow meter, using a flow meter, like an ultrasonic flow meter. You can rent them out there, or you can, sometimes you can just use a bucket, and you can use a 5-gallon bucket, and you can actually, to measure water, to get that good data that we're talking about, you can actually just put a bucket underneath a stuffing box sometimes and collect that water as it's coming out. And then you can empirically show the mill, hey, this is what kind of water was leaking out of the stuffing box. From there, we're estimating that this is going in your process, but we know this much is going to ground, and it's going to drain. And where does it go from going to drain or going to ground? It goes to the wastewater treatment plant. It has to be treated out there, and we know that it's being wasted. But we knew from being able to measure this water that we were getting 4.23 gallons per minute. That's a lot of water coming out. So that was a stock pump. So that stock pump probably had a less than a 4-inch shaft, or right at a 4-inch shaft. Knowing those stock pumps the way I do, that was probably a 4-inch shaft thick stock pump or stock pump. Over a whole year, if that pump operated 365 days a year, that would equal 2.1 million gallons a year that they were wasting just at going to the drain, And so what we did is we then estimated, excuse me, I'm trying to move this one tab all around so I don't see it. There, oh, what just happened? Oh no. There, did that come back? Lori, can you hear me? I'm sorry, my thing just glitched.
It's just your view.
Okay.
Everyone else was still seeing the slides. We're good.
I apologize. It glitched out on me. So the water loss to the process side, which is the dilution, what we call the dilution rate, we estimated that because we knew it was coming to the drain, and we knew it was going to the pump in general from the external source. So we did some math there, and we knew that 1.5 gallons per minute equaled about 262,000 gallons per minute was going into the process. That was stuff they had to evaporate year in and year out, and this was just one pump. So over time, that translated to a lot. Okay, you can go to the next slide, Lori. I'm sorry. So the total loss to doing this poorly was about 2.6 to 2.63 million gallons a year. I mean, that's a lot of water for one pump, and this isn't uncommon at all. It's something that you see regularly in a paper mill quite often. The way we fix this, and just in packing alone, is we took a high performance packing, a carbon braided packing, instead of using like a Kevlar or pure Teflon or what have you. When the gland follower, remember I told you, the better textiles we use, the better material we use, the more that packing can transfer heat. And so we wanted to make sure that we could affect a good gland load by putting pressure on that packing and putting pressure in between the lantern ring and the packing. By doing that, we were able to, we added a great packing. It has a 4,000 feet per minute shaft speed, so that's very high. We introduced a better, more high performance lantern ring. And what I mean by that is you see, sometimes you'll see these lantern rings come out of these stuffing boxes that are flimsy. They're easily broken. They're easily plugged up. We added a high-end lantern ring that had a bigger width, and then on top of it, we added a better flush system. And what I mean by that is we take a line in, we ball valve it off. We use a ball valve to control the flow. The ball valve in controls the flow, and we can measure the pressure at that point. On the discharge side of the flush, we put another ball valve, and then from there we can maintain and dictate what that pressure is, and then we can create a positive pressure in the stuffing box, only allowing a trickle to come out of that flush line, and then we can control the flush coming out of the packing and the gland follower through the mechanical load. So that's the benefit of adding a high performance packing, is that you are able to affect a tighter, more even gland load with a high performance packing and a good lantern ring than you are with a not so good packing like an aramid type fiber, because the tighter you tighten down on that gland follower to affect the leakage rate, the more you're going to get that packing to cause problems over time, meaning it's going to either burn up, it's going to cause wear on your sleeve or your shaft, and then over time it's going to leak even more. But now, so after we did all that, after we put them on the right, we documented through data, we documented to them what they could save. The new system eliminated to the drain. Now I'm talking what comes out of the stuffing box and what comes out of the discharge side of the flush. That was over 2,100,000 gallons per year. That's a lot of water with one pump. The dilution rate into the process, we were able to get it down to half a gallon, just half a gallon a minute per year, and that was over 262,000 gallons per year. We were able to save on the dilution rate. So the water conservation on this one pump that we were able to show, and we were able to get a good cost saving signed off on, was 2,890,000 gallons per year that we were able to document to them and say, hey, this is what we can do per pump if we got the opportunity. Now, not every pump in the plant is going to be that bad of an actor. That was just a particularly bad actor, but you get an idea of what kind of, when we're talking water conservation, and nowadays that we're in such a stringent time where we have to, each plant has to be good stewards of the environment and to show that they're making an effort to get from one bad actor to another, that they're working on fixing that. We can certainly help them do that. Guys, any questions? Love to be able to answer anything. Like you said, the last poll we were a little quiet on, but I'd love to be able to help answer any questions we can.
Hi, we have not gotten any questions at this moment, but we have about 2 minutes left. So I'm going to ask you one question that I thought of. So we're talking about with agitators and mixers and things like that, having to have flush. Is there a technology available for mixers and agitators that doesn't require flush, that might be beneficial to pulp and paper or food and beverage or ethanol or anything like that?
Oh, yeah, absolutely. I mean, so right now there's, air seal technology out there that's just it's just gangbusters. In terms of water conservation, this would be like the best of the best, because you're not adding any water. If water is the enemy, and they're okay to have a little air in their system, just a tiny bit of air in their system, air seal technology is kind of the new wave of where we're moving towards on big hydropulpers, big agitators, mixers, augers, things of that nature, where we just don't want to add any flush water to the system anymore. Air seals are what are taking over right now. We see a lot of that these days.
Okay, well, thank you so much, David, for being here today. Remember, everyone, we recorded this and we will send you the recording and the slides within 24 hours of ending today. And there are 2 handouts in your right-hand sidebar if you want to download those before we close out. And David, thank you so much for presenting today. Great information as always. And we look forward to seeing y'all next month at our webinar that will be talking about food and beverage sealing, and we'll get those details out to you as soon as we can. Thanks again, everybody, and we hope you have a great day and a great rest of July.
Thank you.
Thank you.